Okay, let's talk about minimum spanning trees. So our goals here are to introduce this new topic of minimum spanning trees and to introduce sort of the most common way to solve for a minimum spanning tree called Prim's algorithm. And then we'll talk about proving the correctness of Prim's algorithm. There is an exercise on the website associated with this, and just the first two questions go with this set of slides, and then the third question goes with the next set of slides, which is solving the exact same MST problem, but with a slightly different algorithm, both of which are pretty interesting. So what is a minimum spanning tree? So it's the output if you're given a graph and you collect all points or connect all points together as cheaply as possible. So why is this useful? It's essentially a fundamental graph theory problem, and it has several greedy-based solutions. We'll be looking at two. It also has a ton of applications. So it has applications in clustering, networking, and a lot more. So let me give you one example. Let's say you are designing a new subdivision, and it has the squiggly roads that most subdivisions like to have now to control the speed of traffic. You've got a bunch of houses on that subdivision, and let's say you're trying to wire up internet to all of them so that they are all connected to the internet. Well, you could kind of think of this as a graph, and you could even think of it as like a fully connected graph. Not necessarily the best way well, it is a good way to represent it, but it wouldn't make sense to have all these connections in the final version of the graph. So maybe some of these edges are weighted, or maybe we weight these edges based on like how difficult it is to trench that. So maybe there's a lot of rock here, and even though this is a longer edge, it's easier and cheaper because it doesn't go through other utility lines and whatever. So Prim's algorithm, or the minimum spanning tree algorithms, what they can do is tell us sort of what's the cheapest way to connect all these houses together. So how do you have a minimum connection while also doing it as cheaply as possible? Okay, so there are several greedy solutions to this, and they're optimal solutions, so we won't have to look beyond greedy solutions for this class. There are non-greedy based solutions, a randomized solution, and a couple of others that actually beat what we'll talk about in class. But we'll focus on the algorithms that are sort of the most common to talk about. So this problem was first solved in 1926, and then it was solved again in 1930, and unfortunately neither of these people sort of had it published in a place where it was easily to be seen by sort of the English-speaking world, which is kind of the name of the game in computer science for the majority of computer science, unfortunately. So even though this algorithm was first discovered by Yarnik and Boruvka, we're going to call it Prim's algorithm. For better or worse, that's what it's known as. And then Kruskal's algorithm is a slightly different version of it that came out in 56, and you can see the times here are all sort of interesting. And I won't say, and not all these people were computer scientists. Obviously, this has applications that go beyond computer science, which is why it was of interest to other groups of people. But what we're going to end up with, even if we don't look at the optimal versions of this algorithm, is a blazingly fast output that can run in big O of m log n. And don't forget, it just takes big O of n plus m to read a graph from a file, if it's an adjacency list, for an example. And what's even more impactful is that there are an exponential number of possible spanning trees, and we can choose among all those possibilities in just big O of m log n time. All right, so the last little bit of history that I'll mention here is that in 95, an algorithm, a non-greedy algorithm was created for this that runs in this time. This function here is called the Ackermann function, and that's faster than like the logarithmic function, or it grows more slowly. So if you have a logarithmic function, the Ackermann function grows more slowly. So that is sort of a better algorithm. Beyond the scope of what we'll cover in this class, though. Okay, so let me more formally define the minimum spanning tree problem for you. Your input is a weighted, undirected graph, and a similar problem can be constructed for directed graphs, but normally we'll call that the optimal branching problem as opposed to the minimum spanning tree problem. Each edge is going to have a cost, and the cost in this case can be negative. That's not going to be a problem like it was for Dijkstra's algorithm. Our output is a tree that spans all vertices. And we're going to also calculate the cost as the sum of all edges that are in the tree. And a good place to start with is, what does it mean to span a graph? Well, to span a graph it just means you take a subset of your edges. So if I have this graph, let's say it's fully connected, Let's pretend like I've got that fully connected. I wasn't overly careful there. Not all these edges are useful, so let's just say to make this span, we just need, for example, these edges. So some subset of the total number of edges to make this span the graph. All right, so spanning trees have two properties. They don't have any cycles, and the subgraph is connected. So here's a graph. What is a spanning tree for this graph? Well, there are a number of different spanning trees for this graph. We could take these three edges. We could take these three edges. Point is, there's a number of them. Here's an example of a spanning tree. It's not a minimum spanning tree, but it is a spanning tree nonetheless. Okay, so we are going to make a couple of assumptions here just to make our lives easier. We're going to say that the input graph is connected. That's not much of an assumption. It's pretty easy to check beforehand if we want to. We can just run a breadth first or a depth first search to check for connectivity. If we don't have a connected graph, then you really have a minimum spanning forest, which means you have all your individual spanning trees. And our second assumption is that edge costs are going to be distinct. All the algorithms we'll discuss today will be correct with ties, but it'll make our lives easier as we're comparing and doing our proofs.